Hi, I'm Joel Eriksson from the BitSec R&D team, and these are my colleagues, Claes Nyberg, Christer Åberg, and Carl Janmar. This talk is about kernel vulnerabilities in general and kernel mode exploitation in particular. We'll begin with a short introduction to the topic, followed by several real-world examples and demonstrations of kernel mode exploits that we have developed ourselves. So, why exploit kernel-level vulnerabilities? Well, first of all, the real reason behind most things in life, and perhaps especially here in Vegas, because it's fun. Also, there's not many people doing it yet, so still plenty of bugs around to play with. Exploiting at the kernel level also means that we can bypass most defense mechanisms and any kinds of restrictions such as file permissions, ACLs, secure levels, etc. And since we target operating system itself, we don't have to rely on how the system is set up and configured. There are also a few reasons not to exploit kernel-level vulnerabilities from the exploit developer's point of view. Since any failed attempts will generally lead to a system crash, the exploit needs to be very reliable. Also, kernel debugging can be quite a pain to set up, especially for obscure or embedded operating systems. And of course, in general, we need at least some knowledge about kernel internals. These are some of the common targets for attack in a kernel. For local exploits, there are quite a few potential attack vectors, such as all the system calls, IO control messages, and executable file format loaders, to mention a few. For remote exploits, we are generally restricted to drivers for network interfaces and protocol handlers. Sometimes it may also be interesting with attacks that require physical access. For example, when we want to do live forensics of a system that potentially uses disk encryption, or when we need to bypass a PIN or a password on an embedded device, such as a phone or a PDA. In this case, we also want to look at drivers for hardware interfaces, such as USB devices. As for the payload, we often want to do a privilege escalation, which for Unix-based systems is usually as simple as altering a user ID field. In Windows, we may steal or duplicate an access token from a privileged process. If our userland process is restricted somehow, we can use our kernel mode payload to bypass it, for instance by breaking out of a change root directory. The most powerful payload strategy, and especially useful for remote exploits, is to inject a backdoor directly into the kernel. Some of the things we often need to do in our payload to make it reliable is automatically determining addresses and offsets. This can be done by parsing the L4P headers in memory to resolve the symbols. It may also be done by pattern matching, for instance by searching for certain instruction sequences. As a last resort, we may simply hardcode the addresses and offsets we need for specific kernel releases. For local privilege escalation exploits, there are also some operating system and architecture-specific techniques that can come in handy. Here are some examples of how to determine the address to the process or thread structure pointer on various systems. And as a golden rule for kernel exploits, we need to clean up any mess we create. If the bug we exploited was an overflow, which is often the case, we need to restore sane values for any... Okay. For any important data that was overwritten. For stack-based overflows, we might get away with restoring stack frame beyond the stack data that we have overwritten. And for heap-based overflows, we may need to repair the heap. And now over to our first real-world example, the GDI bug. GDI stands for Graphics Device Interface and is used for handling all kinds of GUI objects, such as windows, fonts, etc. The data for these objects are stored in a memory section, which is shared between user mode processes and the kernel. This memory section is mapped read-only into GUI processes by default, but it turns out that the section can be remapped read-write. Crashing the entire system can be achieved by just overwriting the table with trash, but that's not very fun. So, is there a way to exploit it? As for finding the bug, I didn't in this case. The bug was made public in November last year during the month of Kernel Bugs project. And Microsoft was actually notified about it over 2 years ago, but obviously didn't take it very seriously at the time. Perhaps because they didn't think it could be reliably exploited. When the bug had been public for about a month, and neither an exploit nor a patch had been released, I decided to look into it myself, and after a couple of days I had a working exploit. It was finally patched in the middle of April this year, a couple of weeks after I demonstrated my exploit for it at BlackHat Europe. The first step in the analysis of this vulnerability was finding a reliable way to determine the GDI section handle so we can remap it to gain write access to the section. My basic idea was to find it by pattern matching. If we know the size and contents of the GDI section, we can easily determine when we found it. And this is the first thing we need to know. The GDI section contains an array of structs with these fields, and each entry in the table is 16 bytes large. Combined with the fact that the maximum number of GDI objects in Windows 2000 is 4000 hex, and in Windows XP is 10,000 hex, we can determine the minimum size for a valid GDI section. We may also be interested in knowing how the handle to a GDI object is interpreted. The lower 16 bits of the handle is actually used as the index into the GDI section table, and the upper 16 bits of the handle is used as a sanity check and must match the N upper field for the entry with this index. This is quite useful for us to know when we brute force the handle to the GDI section. My final method is this. We create the GDI object, and we calculate the index where it's supposed to be at by taking the lower 16 bits of the handle to this object. Then we calculate the value that N upper field should have by taking the upper 16 bits of the handle. Then for each memory section that we're able to map, we check the section size, and we get the entry in the table where our GDI object should be. We check the process ID and the N upper fields, and if we're as paranoid as I am, also check the type field. This will have different values depending on what type of GDI object we created. To actually start analyzing the vulnerabilities to see if it can be exploited, I need to set up a kernel debugging environment. Being mainly a Unix guy, I had no previous experience of Windows kernel debugging, but was eager to learn. There were two main options, SoftICE and WinDBG. But since SoftICE was discontinued a while back, WinDBG seemed like the better choice. One problem with WinDBG is that it normally requires two physical machines connected to a serial cable, but this is easily solved by using VMware. Being able to overwrite pointers are always interesting for us exploit developers. And in the GDI section, there are two for each GUI object. One is a user mode pointer used in the process which owns the GUI object in question. The other is a kernel mode pointer used in kernel context. By manipulating these pointers, we hope to be able to eventually achieve an overwrite to an arbitrary memory address. If we decide to target the user mode pointer, we might be able to exploit it through a privileged process, but this would probably be very hard to do generically. And of course, exploiting it in kernel context is much more fun. So, I decided to attack the pkernel info pointer. Since the pkernel info pointer will point to a different type of struct depending on which type of GDI object is being used, I realized I had to try creating different types of objects. It seemed quite likely that somewhere along the line, a call to a GDI-related syscall would eventually turn up writing to something in this struct. After a lot of test cases and a lot of help from WinDBG and IDA Pro, I came up with this. When brush objects are destroyed with the ntgdi delete object app syscall, then the pointer at index 9 is written to with a fixed value 2, but only if the value at index 2 is set and the value at index 0 is set to the object's own handle. As it turns out, this technique was reliable enough to be used for exploiting all of the vulnerable system, which was all the Windows 2000 and all Windows XP systems at the time. There are still a couple of problems to solve before we have a full exploit, though. First, we need to find a suitable address to overwrite, preferably a function pointer. The data that is written to this function pointer will be the fixed value 2, but this is quite enough for our purposes, since we can place the payload on any address in the exploit process. But how do we find a suitable function pointer? To be suitable for us, it must be possible to reliably determine its address. It must also be called in the context of our exploit process. And to avoid a crash, we need to use a function pointer which is very unlikely to be called by any other process while our exploit is executing. The obvious choice is a rarely used system call, which would be very easy to trigger a call to from within our exploit. There are actually two system call tables in Windows, one for the native NT API and one for the Win32 subsystem. My first choice was overwriting a syscall in the native API table, which was quite convenient since there were already documented ways to determine its address. And it worked great, except for under Windows XP Service Pack 1. So, why didn't it work? Well, turns out that this syscall table is actually stored in a read-only memory section, but the read-only property is not enforced in kernel context, except for under XP Service Pack 1 for some weird reason. I wanted something more reliable. When I looked at the other syscall table, I noticed that it's actually stored in the writable data segment of the Win32 module, which is perfect for us, but since there is no documented method to determine its address, I had to come up with a method myself. So, I had two ideas based on pattern matching. This one was not entirely reliable. The final method is to search the code for the call to the function that registers the Win32 syscall table and extract the address from the arguments that are being passed. As for the payload, I want to elevate the privileges of my exploit process, and unlike in Unix-based system, this can be quite complicated. What we do is actually to temporarily steal a so-called access token from a privileged process, and at first I had some reliability issues with this. I'll solve this by restoring the original access token for the exploit process after I'm done. And the final result is a reliable exploit for all of the vulnerable Windows XP and Windows 2000 systems. There were some values that had to be adjusted, but this is automatically done by the exploit. Now time for a demonstration. Okay, so I'll first just show a command line version of the exploit. Let's see. Okay, I didn't have the newest version on this VMware. Yeah, we have system privileges. And we can do stuff like changing the password for the root account, which is the administrator account on this machine. And we can see here that we were an unprivileged user from the beginning, and we can't do privileged stuff. Anyway, I think it would be perhaps more interesting to combine this exploit with another exploit. So I decided to implement it as a payload to another exploit I had written for an Office XP bug that was found by Krister here when he accidentally was fuzzing Office XP instead of Office 2003, which we were targeting at the time. Anyway, I'll open the exploit document. Looks pretty normal. And let's see what happens in another VMware instance here.